guys, this is Professor Janacek, and in the world of directional derivatives of functions in several variables, I want to talk about the maximum rate of increase and the maximum rate of decrease. So first off, don't forget what the gradient is, right? It's the first component, it's the vector whose first component is the first partial derivative with respect to x, and the second component is the first partial derivative with respect to y. And directional derivatives, remember, it's that gradient times with dot product with the unit vector. Now, if that gradient is not equal to the zero vector, then we have the maximum rate of increase of our function at the point AB is the magnitude of the gradient, and it is in the direction of that gradient vector. The maximum rate of decrease of our function f at the point AB is the opposite of the magnitude of our gradient, and it is in the direction opposite of the gradient. I also want to add to this that the directional derivative all right, that's this right here. This is equal to 0 in any direction that is orthogonal to our gradient at the point. All right, so let's take a look at an example. This first example is just a reminder of how to find the directional derivative. So let's compute the directional derivative of f of x equal to 13e to the xy at the point 1, 0 in the direction of the vector 5, 12. So we're going to compute the directional derivative. There's our little formula for that. Of course, that means we have to remember how to determine the gradient. So let's start with that gradient. And we're going to take the gradient of f of x. Notice I determined the gradient in terms of x's and y's, gradient of f of xy, and then I evaluate it at our point. So the gradient, remember, here's our function f. I'm going to take the first partial with respect to x for the first component and the first partial with respect to y for the second component. So don't forget about using the chain rule. The first partial with respect to x is 13y e to the xy. Again, I am using that chain rule there. That's why we have that extra y in there. The first partial with respect to y, now, we end up with 13x e to the xy. Again, using the chain rule gives me that extra x there, right behind that 13. Now, we can evaluate this at the point 1, 0. All right, this one doesn't look like it's going to be too bad. Looks like we end up with the vector 0, 13. All right, so there is our gradient evaluated at 1, 0. So that's the first bit. The second bit is that we need that unit vector. I don't have a unit vector. I have a vector v. So what I need is a unit vector in the direction of v. All right, how do we find a unit vector in the direction of v? Well, that will be 1 over the magnitude of v times v. So remember, we multiply by the reciprocal of the magnitude times the vector. It's a way of kind of reducing out the magnitude, and I just want the unit vector. Don't need the magnitude. Or the magnitude becomes 1. So in this case, that's going to be 1 over the square root of 5 squared plus 12 squared times our vector 5, 12. Let's see, 1 over the square root of 5 squared plus 12 squared, that's 1 over the square root of 169, which is 13. So 1 over 13 times 5, 12. So that gives us 5 over 13, 12 over 13. So there is our unit vector. Here is our gradient, 0, 13. So we want the dot product. So, oops, where do we go? Here we go. So the directional derivative of f evaluated at 1, 0 in the direction of u is simply that vector 0, 13 dotted with 5, 13, 12, 13. So remember the dot product, lots to remember in this. So there's our dot product. We multiply the first components and then add that to the product of the second components. Put all that together, multiply, add, we end up with just a 12. All right, so that's how we find a directional derivative. Now, let's use that here in example 6. Let's use that technique at least. We want to determine the unit vector that gives the direction of steepest ascent and steepest descent for the function f of xy is equal to x squared plus 4xy minus y squared at the point 2, 0. So the direction of the steepest ascent and steepest descent, well, that's going to be just our gradient vector. Notice that is the direction of the rate of increase or the increase and the direction of the decrease. So that's what I'm looking for. I'm looking for the direction here. So that's why I'm looking for just this piece or this piece. Actually, well, both of them. All right, so that's what we need. All right, so yet again, we will start by finding the gradient of this. The partial derivative with respect to x is 2x plus 4y. For the first component, the second component, what is that? 4x minus 2y. And now we simply evaluate that at our point 2, 1. So that gives us 2 times 2 plus 4 times 1 for the first component, and 4 times 2 minus 2 times 1 for the second component. Do all those computations and we end up with 8, 6. All right, now if this were just asking for a vector that gives us the direction of steepest ascent and steepest descent, well, this is the vector that gives us the direction of steepest ascent, and we would simply take its opposite to find the vector that gives us the direction of steepest ascent. However, it's not asking for just any old vector. It's asking specifically for a unit vector. So how do we find a unit vector? Well, we want the unit vector in the direction of 8, 6. Remember how to do that? We did this up here. Unit vector in the direction of some vector v is 1 over the magnitude of that vector times the vector. So we end up with 1 over the magnitude of 8, 6. That's going to be 8 squared, square root of 8 squared plus 6 squared times that vector 8, 6. So we end up with, let's see, 1 over the square root of 100. So that ends up being 1 over the square root of 100, 1 over 10 times 8, 6. That gives us the vector 4/5, 3/5. right, so there we go. The direction of steepest ascent is 4/5, 3/5, and the direction of steepest descent is the opposite of that, -4/5, -3/5. All right, well, there you go. Not too bad. Oops. Things got moved a bit. Oh, not sure what happened there. All right, well, we're almost done. I do want to add one more thing to this. There we go. I want to add one more thing to this, and that is, now that we've got this, can we determine the vector, or I should say a vector, it might not be that points in a direction of no change? Well, what we're really looking at is to determine some u such that the directional derivative at this point 2, 1 is equal to 0, which means we need to determine this u1 and u2 such that our directional derivative, which of course is going to be this unit vector, this vector 4/5, 3/5, dotted with this u1, u2, is equal to 0. Well, that means 4/5 u1 plus 3/5 u2 would have to equal 0. So we could choose, anything that would work. So we could choose 5/4 and -5/3, because if we put that in there for u1 and u2, we get 0. Or you could choose, there's all kinds of options, -3/5 and +4/3. That would also work. Number of things you could choose, but that's the idea. So if you're looking for no change, remember that means the directional derivative is equal to 0. Well, there you go. Enjoy.